started projecting his voice. All right, we're gonna start. So, recording?
Yeah.
Awesome. So, this is an interesting class because, like, I don't know, I feel like we have like all of our classes at the beginning and the end of the week, you know, even though there's like only one day in between. It just feels a little weird to me. I don't know. Anyway, so as far as I'm aware, there are no housekeeping issues. The test's coming up in a couple of weeks' time. There's time to talk about that, though. You know, we still have some time to figure that out. So, just a reminder: this course does have a midterm, and we're going to be writing it at some point in the near future. But you know, I imagine you probably have at least one test before that. So you know, so it goes. Earliest test first, right? No? No? You're free and clear? Ah, well.
A weekly physics test.
This will be your first midterm ever?
No.
Oh, okay. All right.
Yeah.
That would have been very exciting for me.
Skip the second.
The only math to Z are free as midterms other than this course for us.
Really?
Yeah, but we have weekly physics tests, so you don't have to make it harder, it's okay.
I mean, weekly physics, but that's more like if it's weekly, it's like a quiz, not a proper like.
It's like a unit test.
It's also 2 courses and
Yeah.
8 units
Yeah.
that combined have a weekly test. So
Yeah, it's not great. It's and like hard assignments.
Good lord. Well, I guess like it's kind of interesting because this test will also not be a traditional test in the traditional sense, you know, because it's going to be a programming test that you do on your laptops. So, you know, there's going to be some special procedures for this one, but again, we don't have to worry about it yet. Let's worry about pointers, okay? Pointers like this. Pointer. Anyway, so pointers are a very, 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 very highly important topic in C. Learning pointers is kind of the entire point of studying C as a language. I may have mentioned this last time, but the thing about C, to be a proper C programmer, you must be able to work with pointers, whereas most higher level languages hide these details from you because they are difficult. That being said, if you want to be a good programmer in most languages, most particularly things like Java and C++, you still do require the same knowledge that goes into pointers. It's just hidden in various ways, right? In various other languages, we would be talking about references, or in Python, aliases. In C, pointers are a little bit different than what you might imagine from sort of your typical object-oriented language. Most object-oriented languages sort of deal with pointers in the sense that if you have an object, right, that's a reference to you know, some region of memory that contains some variables, and it comes bundled with some functions, right? But like the object itself is generally thought of as a reference to an object, right? Rather than, you know, you can sort of squint and think of it as the object itself. That's the intention, but, you know, the set of operations on objects kind of expands to the point where it's obvious that they're pointers at some point or another. But anyway, pointers in C are different because the things that we're pointing to are your normal, average, everyday data types, right? We point to integers, we point to characters, we point to, you know, structures once we get there, right? So it's very, very important to understand this point. It's kind of like this is the one point that is absolutely essential that you understand. A pointer is a variable whose value is a memory address rather than directly the value of the variable. So I'm going to do a bit on the board. Oh, I should have better board lights than this. Let's see here. All right. So in order to understand how pointers work, you really have to understand how memory works, right? So in your typical computer system, you have your CPU, right? You have your external memory unit, generally represented by a cylinder, even though, you know, this will often be RAM chips, but, you know, whatever. How is data actually accessed from memory? The answer is on the slide. Every single slot which can contain a byte inside of your memory system has that byte addressed via an addressing system, right? So you can kind of think of your memory as a big, you know, rectangular array or a linear array of cells. Each cell has a particular address, you know, starting at 0 and going up to however many cells you have in total, right? Generally, these things are byte addressed. So every 8 bits, you have a different address value, right? So, you know, if I pick some value out of the middle, that might be an address, you know, FFA37C or something like that, right? Memory addresses are typically expressed in hexadecimal. So what we are doing when we are working with pointers is we are manipulating these memory addresses themselves. This is distinct from the values that are contained in memory, right? This is the key, this is the value in sort of, you know, Python dictionary terms. Make sense with me so far? So the thing which is interesting about pointers is that they expose the ability to look up values in memory directly by a memory address, right? So this means that we need a different and distinct data type to represent these pointers. Basically, you know, a large number of seg faults, which are not caused by, you know, overrunning the bounds of an array, probably I'd say 80% of seg faults, are caused by dereferencing memory that is outside of the scope of the memory allocated to your program, right? So basically, what the operating system does, there's a region of memory inside of your general memory system which has been given over to the program that you're running, right? A pointer dereferencing operation will give you the value at a particular address in memory, right? For whatever address you're dereferencing. If the address that you're dereferencing happens to fall outside of your allocated zone of memory, your operating system detects this as a segmentation fault. You're trying to read memory that doesn't belong to you, right? Thus, program crash, right? So, this is the inherent danger of pointers. And I know we're not as far off the slides as you might think at the moment. So the problem with memory addresses is there's very little overlap with the types of numbers that you would typically use in a typical program. They tend to be very large because the region of memory you're allocated tends to be fairly far down inside of the chip, right? So, you know, your program that, you know, only works with integers between 0 and, or negative 10,000 and 10,000 probably is not ever going to have a valid memory address inside of your memory region that you're actually working with, right? So dereferencing a regular integer will cause a segmentation fault, you know, the overwhelming majority of the time. It would be extremely surprising if, you know, dereferencing an integer didn't cause a segmentation fault, right? So, in order to aid the programmer in their ability to work with pointers correctly, we have a dedicated pointer data type. C will do a certain amount of checking to see whether you're using pointers correctly, give you warnings if you're dereferencing something that isn't of a pointer data type. But again, once again, the underlying representation that is given to pointers is the same as pretty much everything except floats. It's just an integer under the hood. It's just binary data. There is nothing technically or physically preventing you from dereferencing a regular pointer. This will a lot of the time show up as a compiler warning, which again, that's why it's so important to pay attention to your warnings when you're programming with C. So, to declare a pointer data type, it's very simple. You take a regular data type and you affix the asterisk character to the end of the data type. This indicates it as a pointer to a value of this data type. So you might be wondering, why do we have this interesting phraseology where we're modifying an existing data type in order to sort of give us a pointer? It all has to do with how many bytes the dereferencing operation has to fetch, right? The number of, how many bytes is a character in C?
4.
Oh, how many bytes is a character? 1. How many bytes is an integer?
4.
Yes, 4. How many bytes is a long integer? 8. So, in order to dereference the memory and extract out the value stored at that memory, it has to know how many bytes it's extracting, right? So, if you have an integer pointer, a dereferencing operation will extract 4 bytes from memory. If you have a long integer, it will extract 8 bytes from memory. It's actually possible to split a long integer into single bytes by placing it in memory and then having the C program pretend it's a character array. And then you can read out the individual bytes using regular addressing, which is kind of cool, right? There's nothing inherent about the memory which makes it an integer or a character or a float. It's all the manner in which the computer reads the memory, right? It's the context that provides the data type. There's nothing inherent in the memory itself that does that, at least not in C. Am I making sense so far? So, this is why we pointerize data types to declare variables of pointer data types rather than just having like a pointer keyword that we throw in and then it's just a pointer. Very brief side tangent. On the subject of pointers as applied to existing data types, it is possible to construct a pointer that does not have information provided about how many bytes it should read out of memory. These are known as void pointers. So the void data type, you apply a pointerization to it and you get something that doesn't know how many bytes it's supposed to read. Therefore, to dereference a void pointer is an error, right? So what's the use of void pointers? You can cast them as other types of pointers, right? Have we talked about casting? No? Oh, well, it doesn't really come up very much until we start talking about this sort of thing, but casting is how you convert between different types in C. So basically, you know, if you have a data type like, you know, let's say you had a short int x equals 3, right? And you had a regular int y, right? You can cast, actually it kind of works in the better in the other direction, but you can cast x as an integer by providing a data type in parentheses before the expression, right? So what that does is it forces the outcome of this expression to be the data type you specify, right? So whatever x is, it's going to read it as if it were an integer, right? So, for example, if you went the other way, if you cast an integer as a short integer, it'll take the first 2 bytes and throw off the second 2, right? So that's casting. You can cast with pointers as well, but what casting means with pointers is changing how many bytes the pointer is reading from memory when it dereferences. Have I lost anybody yet? Yeah? Okay. Questions?
When you say dereference, is that just extracting the data from wherever, like the memory address that the pointer took you?
Yes. We have lots of slides on dereferencing, but dereferencing is the operation by which you take a memory address and look up the value stored at that memory address in memory and return that as the result of the dereferencing operation. Right? So memory address goes in, the value pointed to by that, or the value stored at that memory address comes out. Make sense? Question?
What's the benefit of pointers when if you had an integer that was 0, wouldn't it take up more processing to be like, oh, look at this memory address, then convert that 0 and just say the variable 0?
So the question is, what is even the point of all of this, basically? Yes, you're absolutely right. If all you're dealing with is single variables, pointers are pointless, shall we say. What pointers allow you to do is build complicated data structures, right? So, motivating example time. This is jumping ahead in the course substantially, but we'll do it anyway. So, for example, you've heard me talk about binary trees, right? So how would you do with that with an array? So this is one of the things you use pointers for. You can declare a node type, right? So you can say, I have a node structure, right? It includes an int value. It includes a node pointer next, or not next, left, and node pointer right. Right? So, what you can do is you can then instantiate many of these nodes, use these fields, like you take the left field of this node and the right field, right? You assign to this field the memory address at which this node is stored. That effectively creates a link to this node, right? Link to that node. These guys link to more nodes, right? This allows you to build more complicated data structures, right? And basically anything more complicated than an array is going to require pointers at some point. The other thing that, like the very, very traditional application of pointers that we're eventually going to talk about is the linked list. So arrays have certain advantages, but they also have certain disadvantages. If you want to insert a value into the middle of an array, you have to basically move every element in the array down by one past the element that you're inserting, right? Also, dynamic expansion and contraction of an array might, in some cases, require copying all of the array into a new segment of memory, because arrays must be maintained in continuous memory. Because a linked list does not, in a linked list, it's like this, every node points to the next one, right? So in memory, these things can be stored anywhere, and they just kind of point to each other, right? That means that the amount of memory you have to set aside for any particular node is very small. And when you need to delete a node, you only need to deallocate that memory and reassign the pointer. And then that's a much faster operation than deleting and resizing an array. So for dynamic data structures, that is to say, data structures which change their size frequently during execution, the only way to do that efficiently is with pointers. Does that make sense? So right now, we're working with pointers on things like integers and floats so that you get the concept of how a pointer works. Very quickly, we're going to see that pointers are also how arrays work, right? So again, jumping ahead a little bit, we're going to see that pointers are actually how arrays work too. So if you have, an array in memory, let's call it A. When we have just A itself, that is a pointer to the first element of the array in memory, right? So A is in some sense equal to A at 0, right? We're going to see that basically, A is a memory address, let's say 0x88, right? The next cell is 89, then 90, etc., right? So, A at x is equivalent to a dereference of A plus x, right? You take this guy, you add this to the existing memory address of the array, that gives you the offset. That's how arrays are actually read, people. This square brace notation actually is just syntactic sugar for array offset calculation plus dereferencing. And that, my friends, is why most programming languages index starting from 0 for their data structures. Because the first element is offset 0. So it's not index. You should, if you're thinking about things clearly and correctly, it's not I am accessing element 0, the 0th element or the first element. I am accessing memory with offset 0, with offset 1, with offset 2. Make sense? So that's what pointers are good for. Any questions? Yeah.
Just a quick question about the node example. Can can you add as many pointers to that node as you want? Like, say you wanted
Yeah.
to be able to go up the tree, you could have another pointer go like up.
Absolutely, that would be a doubly linked tree. Yeah, absolutely. You could, it gets very complicated. You can also have the node contain an array of pointers, right? So you could have nodes which point to an arbitrary number of other nodes, right? That would be an expression of a general graph. And we'll talk a little bit about graphs, but we'll save that for your course on data structures. Okay? Any other questions? Okay, so moving swiftly on. The star character indicates that PTR, which is the variable name, is an integer pointer. This is to say, pointer points to a segment of memory the size of an integer. The star character may be applied to either the data type or the identifier itself. So you can put it here, you can put it there. In this particular example, this only count pointer is pointerized. If this were applied to the integer phrase, count pointer would still be the only variable pointerized. So don't declare pointer and non-pointer variables on the same line. The rules are a little bit confusing and they don't make sense, so just avoid it. Okay? Question?
Since white space doesn't matter, those are exactly the same thing, right? The having before the space and after the space? Or am I wrong?
So white space, like,
Or it does?
yeah, okay. Yeah, that's probably, yeah. I'm trying to think of if it's actually true that it never uses white space. And I'm thinking that is actually possibly true, that it never, ever, ever uses white space. But yeah, good call. Question?
I'm kind of building off of that. It's like if you wanted to, could you put a space in between, like you can do in space, the asterisk, and then space between whatever you want to call it?
Possibly. I'll leave that I'll leave that as an exercise to the reader. If you put a space in the middle of a variable name, that's a problem. Yeah. So there is a very slight degree of white space sensitivity, shall we say? But again, just program using the conventions and nobody gets hurt. So, in blue Blockovision, we might have some variable count, which has value 7, and count pointer is a thing which points to 7. Two things to note about visualizations of pointers. Number one, they are typically done with arrows. Number two, if you're programming in using Python Tutor, the C version of Python Tutor, it will in fact put little arrows inside of your data visualization, which is extremely helpful. So if you weren't using Python Tutor before, I highly recommend using it now. Okay? So, pointer facts. You can create a pointer out of any data type, including custom ones. The star means something different when you're not declaring a pointer. It's not part of the identifier. So, just because you have like star count pointer here does not mean you use that star every time you use count pointer. It means something else when it's inside of an expression, right? Specifically, that is the pointer dereferencing operator. We'll get to it in a couple of slides. So, since pointers are a more direct manipulation of memory, you can squeeze some efficiencies by squeezing in some pointers. So, you can make your programs more efficient if you know how to work with pointers. Normally by introducing clever data structures. Stylistic points. To avoid the confusion on the previous slide, it's better to declare pointers and direct variables on separate lines. Putting some indication that a variable is a pointer in the identifier is a good way to be able to tell which variables are pointers later on. If you have a pointer call it a pointer in the variable name, please. It helps a lot. So, like a lot of things in C, uninitialized pointers contain junk data. So, just like any uninitialized variable, it contains junk data to begin with. What is the likelihood that junk data will happen to fall inside of your given memory space if it's dereferenced? Very small. So dereferencing a pointer before it's been declared with anything is very, very bad and will cause your program to crash almost immediately. In general, pointers should either be initialized to 0, null, or a value that makes sense for the program, like some valid value, whatever that might mean for the program you're writing. Null is something that we haven't quite seen yet in C. Anybody familiar with Java? So you guys will know that Java uses null quite a bit as well. Null in C is a little bit different from null in Java. It is literally just a define statement in the standard library that sets null equal to 0. So everywhere you write null in your code, the preprocessor goes in and replaces it with 0. So null equal 0 comes out true in C, whereas I'm quite sure it comes out false in Java, though I might be wrong about that. Make sense? Right. So null is a symbolic constant which is defined in a number of header files such as standard IO and standard definitions. Null is the same thing as 0, but it's preferred for stylistic reasons because, we talk about null pointers rather than 0 pointers because, it's presumed that a pointer pointing to 0 points to nothing rather than pointing to 0, right? Make sense? A little bit? Anyway, so, good. So, now we know how to store these things. We know how to create variables for them. What good is that if we have no addresses to store? Memory addresses are accessed using the ampersand address of operator. This is a prefix operator, all right? So it functions in the same way that the negative sign turns a positive integer negative, or the bang symbol turns a boolean from a true into a false. The ampersand turns anything into the location at which it is stored, right? So it's the inverse operation of dereferencing, right? So, applied to any identifier, it returns the physical memory address of that identifier, and this includes pointers. So, this is where things start getting interesting. Because pointers are also variables which are stored in memory, a pointer itself has a memory address, which means that you can create a pointer to a pointer. You can create pointers to pointers to pointers to pointers to pointers, right? Visualizing that, if we have memory, let's say we have int x equals 7, right? So 7 with address, 37, sure. How these variables are actually stored by the program, by the way. Your program keeps a table of them. So x is being stored at 37, right? If we then say int star x pointer is equal to the address of x, this is what goes on. We declare a new separate piece of memory, right? We store in it the value of x's address, in this case, 37. Let's say this is in 84, right? Then this gets registered in our table. X pointer, 0x, 84. So what this ampersand operator is actually physically doing is it's looking up what the stored address is of the variable with respect to this table which the program is maintaining, right? It's just looking it up in the, variable names to addresses table. Make sense? So, we represent that normally with an arrow. If we were to go one step further, int star star, x double pointer is equal to the address of x pointer, right? We declare new memory for this. We store this value here, which is 0x84. We store that at 92 or whatever. And then we store x double pointer with address. We associate that with address 92 in our symbol table. Does that make sense? Is there, you have a question?
So if you reference double X pointer, you would just get the memory address of
X pointer. Yeah. Yeah, exactly. So what a dereferencing operation is, right? To dereference X double pointer, right? We take the value stored at this address, right? Treat that as a pointer and follow it to memory. So the dereferencing operation only requires the symbol table insofar as it's looking up where to look up the point, where to find the value, right? Just like a regular variable reading operation. How's it going, everybody? Good? Is this making any degree of sense whatsoever? Okay. Question?
Could you just quickly explain what the double star means?
Yeah. So the star is associative, right? So it's just that, but with the brackets left out. Like that actually is technically how it is. It's a postfix operator. So it's like I want a pointer to something the size of an integer pointer, right? Integer pointers are actually quite a bit longer than integers themselves, right? The size of a pointer, like basically all pointers are the same size. They just gather different numbers of bytes because what the pointer is pointing to is memory, right? So whatever your maximum memory address is, however many bits it takes to represent that, that's the size of all pointers, right? So it would be incorrect for a dereferencing operation on a double pointer to read the number of bytes contained in an integer. You want the number of bytes contained in a memory address, right? So that's why double pointer. It's a pointer to an integer pointer. Make sense? Question?
So does the pointer point to the memory address that has the integer stored in it, or does it point to the integer itself?
The pointer always, like the integer itself is a cell in memory, right? So X pointer, right, stores at this memory address, right? If you dereference this memory address, you get 7. It's kind of like a little bit of a sneaky little tactic. Every single time you've used a variable so far, you have actually technically been performing memory dereferencing, right? It's just the address that you are dereferencing is being stored in a symbol table rather than being something you can directly manipulate in the program, right? What pointers allow you to do is to directly manipulate those memory addresses yourself, rather than relying on the symbol table. Make sense? Yeah. Technically speaking, you could write an implementation of variables in your program using by declaring one big array and then just using pointers for everything. If you really wanted to, don't recommend it. Yes?
Well, I just can't read that. What do you call the variable that points to the first one, to the nodes?
Oh, sorry. This guy?
The last one.
XD pointer, the D standing for double. I know my D's kind of look like O's. I apologize for that. Question?
If you had another pointer pointing to the last pointer, that would still be a double asterisk, right?
No, that would also, they would be of the same size, but if you, C does keep track of the nestedness of the pointers. So if you wanted a pointer to a double pointer, that would be a triple pointer, right? And you would declare it int star star star, right? It's a reference to a reference to a reference to an integer, right? In this course, I think double pointers might be the furthest we get. I don't know I can't remember if we ever deal with triple pointers, but yeah. Question?
Yeah, just how far could you go with how much of a change can you make with references?
Infinitely. Infinitely. Yeah.
Really boring.
Yeah. Theoretically, it depends on how many asterisks you want to type. There's really not okay, so typical uses, right? Single pointers are usually used for arrays, right? Double pointers are often used for references to arrays, right? One use of pointers that comes up reasonably frequently in the standard library is the passing of values out of functions via mechanisms other than return. So implicit return values are also done via pointer, because if you pass a reference into a function, that function can directly write into the memory cell it's been passed a reference to, which allows essentially you to be able to write to variables inside main from a function without needing a global variable, right? So if you're doing that, if you're trying to do an implicit pass on a double pointer, then you would need a triple pointer, right? It's stuff like that. I don't think I've ever in my life encountered a quadruple pointer, right? Or seen any reference to them. So, because the uses of that become so obscure, you know? But anyway, we still got 5 minutes. I hear the bag zipping. Jeez. So, anyway, this is basically what I already did. The inverse of the ampersand operator is pointer dereferencing. It's a little confusing. Pointer dereferencing is also the star. I would have picked a different symbol personally, but then again, I'm sure it made sense to Dennis Ritchie at the time. Also, the format tag for pointers is P. So, and that just automatically will display it in hexadecimal. So if we have this small program, int y is 5, int star y pointer, we store the address of y in y pointer using y pointer is equal to ampersand y, Then printing, the pointer's value is this, the value pointed to is that. We get this long hexadecimal thing, and then we get the 5. Notice the star here. This is an expression, so the star is here interpreted to mean a dereferencing operation. Make sense? Good. Question?
I don't know if I have this right or not, but if are arrays pointers themselves, like is that?
Arrays are pointers like with certain attributes read-only.
So if you were to point to an array, are you technically dereferencing the array and getting the value?
Yeah. Yeah, like when you write, A at 5, right? A is a memory address. It's adding 5 times the byte width of the data type to that memory address, and then performing a regular dereferencing operation to return that element of the array to the rest of the program.
And all of that is then just declaring it as an array. All of
Yeah, you don't have to declare it as a pointer, though you can declare arrays as pointers and use them as arrays. Question?
So for earlier, when we were talking about pointers,
Mhm.
is it an arbitrary selection for 0x92, or is there a reason behind it?
That's determined by the operating system, roughly speaking. So the question is, where do these addresses come from? Right? Why did I essentially choose random values here? These values are essentially random. First of all, the region of memory that the C program is provided is essentially random as it's provided by the operating system. It depends on what other programs are running, how much memory they're using, what operating system you're running, what your background processes are. Lots and lots of factors go into it. And then within the memory segment that your program is allocated, that's also essentially random, which, it's arbitrary but deterministic. Mere mortals cannot understand the depths of the algorithm by which this memory is allocated, so it's best to think of it as being random, but computers are not capable of true randomness, right? So it makes sense to the computer why it's giving you this particular address, but you will have no idea why. Make sense? Any other questions? Yes?
To essentially alter the pointer's location, that address, could you add 1, or would that result in a segfault because you might be reaching into a memory that doesn't belong to you?
Adding 1 to a regular variable will get whatever memory comes after that variable in the same way that reading past the end of an array will. Right? It's you can almost think of variables as being arrays containing one element in this sense. So, yeah, you can read past the end of these things by modifying the pointer. Yeah, and that's the value of pointers. That's one of them, right? It's because we have elevated them to the level of just some math that we're doing, just like all the rest of the math we're doing, we can apply things like addition to them, which allows us to scan through memory, right? And that is how arrays work. Make sense? Was that your question?
No, I was just, what if you're trying to multiply 2 pointers?
Oh, that's not a permitted operation. Addition and subtraction are permitted operations. Multiplication is not defined for pointers, because what does that even mean?
Right.
Right.
Because if the value's 5, it's going to multiply by 10. You couldn't do that.
Well, you could, yeah. You just do times 10, and that also uses the asterisk.
Right. So if it was that multiplied by another pointer that was 210, could you do would it be star?
Oh, yeah.
Times star thing.
Yeah, it would probably just do it and give you nonsense, and you just have to deal with the nonsense. Mm-hmm.
Is that a bunch of stars? That is basically.
I don't want to say yes because that sounds like a really bad heuristic.
Gotcha.
All right, thanks, folks.